Hello everyone, welcome to this lecture. In the previous lecture, we studied free and force vibration of single degree of freedom systems with viscous damping. In this lecture today, we are going to talk about vibration of single degree of freedom system with structural damping. So, we are going to talk about vibration of single degree of freedom system with structural damping. So, what is structural damping? Let us try to answer this question first. Let us take a simple example. Let us say we have a cantilever beam like this, and let us say it is disturbed and it is vibrating under free condition, right. So, if you consider the free vibration of this beam, then we see that the vibration amplitude, it continuously decays like this, and then the beam comes to a vibration becomes 0 after a certain amount of time. So, in this case the energy loss due to viscosity, due to viscous forces and due to dry friction is negligible. But then what is the source of energy loss then? The main source of energy loss in this case is due to loss of energy inside the material. Okay. So, there are some the damping forces which are acting inside the material which are causing energy loss. So, there is loss of energy inside the material. Or structure. Now, this loss occurs due to work done against molecular friction, and there are some complex processes which occur when material deforms, and therefore work is done against these forces and which causes basically the dissipation of energy, and this is basically called structural damping. So, if you so what is the evidence that such a energy loss occurs inside the material? If we perform a cyclic loading test, of a structure, and let us say we again take this bar subjected to a cyclic load like this f of t, right, and at some let us say we apply a harmonic force like this f naught cos omega t, and if at any point if we draw the stress versus strain, then it is seen that when the load increases, right, then let us say if this is the path being followed when the load is applied, and if the load is reduced or withdrawn, then it is seen that it follows a different path like this. Okay. And when load reverses the direction, it goes in this direction, and again when the load is increased, it follows this kind of profile. So, therefore, this path is continuously repeated. So, what we see is that it forms a closed loop, and this is called hysteresis loop. So, ideally speaking, what may happen is that the stress strain plot, the path followed during loading will be same as path followed during unloading, like this, right. So, this path will be continuously traversed, the same path is followed by loading and unloading processes, and this is the ideal case, and this is something it occurs in practice. So, in practice what we see is that a hysteresis loop is formed by stress strain plot, and this basically occurs because there are some forces, energy dissipating forces which are inside the material, because of which there is a phase lag between the stress and strain, and this phase lag is responsible for the paths followed during loading and unloading processes to be different, and the area of this loop basically represents the energy loss. Okay. So, the area of the hysteresis loop represents the energy loss, right, per unit volume. Okay. So, that is the area of this loop represents the energy loss per unit volume, and that energy loss is occurring basically to perform work against the forces which resist the deformation, dissipative forces, and this basically is nothing but the evidence of existence of structural damping, and that is why structural damping is also referred as hysteretic damping or also internal damping, because this damping arises due to energy loss internal to the structure. So, now how can we quantify structural damping? So, let us go to next page. Quantification of structural damping. So, structural damping is quantified based on the energy loss which occurs in a cycle. So, a index is defined called loss factor represented by eta, right, and this eta is equal to the energy dissipated right per unit radian of the cycle divided by the energy at the beginning of the cycle. So, here ED is the energy dissipated in a cycle, right, and U is the energy at the beginning of the cycle. So, therefore, loss factor tells the fraction of energy, total energy system possesses, which is lost by the system while vibrating, right, per unit while completing per unit radian of the cycle. Okay. The fraction of the total energy lost per unit radian of the cycle, that is nothing but the loss factor. And for some common engineering materials, the loss factor values are like for aluminum, the loss factor is of the order of 0.0002, something like this. and for steel the loss factor is in the range of 0.002 to 0.02, and for concrete the loss factor is in the range of 0.02 to 0.06, and for rubber, these are some of the common engineering materials, it is 0.1 to 0.9, right. So, this is the nothing but the value of the loss factor. So, we see that for metals the loss factor is not so large, okay, which means that the energy loss inside a metallic structure will not be very large. But in structures like made of concrete structures or structures made from rubber or polymer, the loss factor is relatively much higher, which indicates the presence of the mechanisms which cause dissipation of energy inside the material to be quite strong. So, now with this introduction of structural damping, let us now consider a system with structural damping, a single degree of freedom system with structural damping. So, first we consider the force vibration of a single degree of freedom system with structural damping. So, therefore, to write equation of motion for this system, we require the knowledge of the damping force due to structural damping, right. So, structural damping force. So, that is something we need to know in order to write the equation of motion. And in the absence of any suitable model to quantify structural damping force, the damping force due to hysterical damping, what is done is that we try to determine or define what is called as equivalent viscous damping coefficient, and then from that we work out the damping force, because for a viscous damping model we know the damping force, and therefore, if we can determine or define an equivalent viscous damping coefficient corresponding to a system with structural damping, then we can determine the damping force. So, therefore, we try to define what is called as equivalent viscous damping coefficient. Okay. And this is defined based on equivalence of energies, which means we try to determine how much energy is lost in a cycle when structural damping is there, and how much is the energy loss which occurs if viscous damping is there, and then we try to equate these two energy dissipations so as to arrive at what we call as equivalent viscous damping coefficient. So, let us first of all consider the energy loss in structural damping, right. So, if I represent the energy loss in structural damping by say E d say H, right, H for hysteretic. So, this represents energy loss per cycle with structural damping. And it is seen that experimentally it is found that this energy loss EDH, okay, it is proportional to the square of the amplitude of the displacement. That is what it is found experimentally, that it is proportional to square of amplitude, and it is not dependent on the frequency. It means if you change the frequency of the loading, then the that energy loss that does not change, and therefore EDH can be written as say alpha times A square, where alpha this alpha is the constant of proportionality. Okay. So, this is nothing but the energy loss expression for system with structural damping. Similarly, now we would like to work out what is the energy loss or energy dissipated when viscous damping is there. So, EdV, let us represent this to represent energy loss per cycle with viscous damping. So, this energy loss can be found as integration of force into x dot. So, that is nothing but the power, right, force in F into the force into velocity. So, damping force into velocity is the power loss and multiplied by dt, and if you integrate it over one time period of the time period of the cycle of the vibration, then we get the energy lost in viscous damping. And we know that Fd is nothing but damping coefficient multiplied by x dot into dt. So, we need to find this integral. And if we let us go to next page. If we assume that the displacement of vibration x of t is given by say a cos omega t minus say some phase theta. So, let us say this describes the vibration of the system with viscous damping, and if you now find that integral, we obtain this result. So, if you substitute x of t there, differentiate it to find velocity and then integrate with respect to time and then apply the limits, then we get basically this expression pi c omega a square. So, this shows that the energy loss due to viscous damping is proportional to square of the amplitude, but it is also proportional to the frequency of the motion or frequency of vibration omega. Now, to define equivalence, what we do is that we equate ED H or EdV is equal to EdH. We equate these two energy dissipations per cycle, and if we substitute there is the expressions for both, then we get alpha s square, and so this gives us C upon alpha upon pi upon omega, right. That is the result we get, that C is equal to alpha upon pi into omega. So, this is nothing but, and if we represent this alpha by pi as h, so this C is nothing but we can call as CEQ or equivalent viscous damping coefficient. That is what we get. Okay. So, CEQ is nothing but equivalent viscous damping coefficient, and H, which is equal to constant proportional to alpha upon pi, is referred as structural damping coefficient, structural or hysteretic damping coefficient. So, we see that the equivalent damping coefficient is related to the equivalent viscous damping coefficient is dependent on frequency omega. So now with this definition, now we can determine the damping force, because if the equivalent viscous damping coefficient is CEQ, the damping force, equivalent viscous damping force would be simply CEQ into x dot. So this allows us to basically write equation of motion. So let us go to next page. So now if for a system with viscous damping, for a system with viscous damping, we can write the equation of motion as mx double dot plus cx plus cx dot, sorry, cx dot plus kx is equal to f of t, whatever the force is given. So this is the equation of motion, and this is true for any f of t, right? Any f of t, which means it can be an harmonic force, it can be a non-harmonic force, a periodic force, an impact force, any force. This equation is true. But now we cannot directly straight away use this equation to find an equivalent equation for structural system with structural damping, okay, because the equivalent coefficient that has been defined, it is at a certain frequency omega, okay. Therefore, what we do is that we first do a we take a Fourier transform of this equation, So of course, Fourier transform we will study in more detail in a lecture later, but so if we take Fourier transform, then this is going to give us m omega square x in the frequency domain omega plus I c omega x omega plus k x omega is equal to f of omega. So here x of omega and f of omega are nothing but the displacement and force in the frequency domain. So they are defined at a certain harmonic frequency omega, that is what basically it means. Now this equation now is in the frequency domain, right. So this equation is in the frequency domain. So now we can replace, because the equivalent viscous damping coefficient was also defined at a frequency omega. So now we can replace C with CEQ in this case, right. So therefore we can write down m omega square x of omega plus I CEQ, right, omega x of omega plus k x of omega is equal to f of omega. And if I now substitute CEQ here, which is equal to h by omega, then we get plus I h x omega plus k x omega is equal to f of omega, okay, which can also be simplified as minus m omega square x of omega plus k plus I h x of omega is equal to f of omega. So, so this is nothing but the equation of motion in the frequency domain for a single degree of freedom system with structural damping. And what we note here is that now the coefficient of x, the displacement, is k plus I h. This is basically referred as complex stiffness, right. So this k plus I h is basically called complex stiffness. So complex stiffness basically takes into account the force due to the stiffness plus force due to damping in it, due to structural damping in it. That is nothing but the complex stiffness. And so now in order to find the steady state response, we can simply obtain that as f of omega upon k plus I h minus m omega square. So, that basically becomes the amplitude of the steady state response, which is the complex amplitude. So, if we have let us say a harmonic force, say f of t is equal to f naught e to the power say I omega t, let us say a harmonic force is acting on the system, and therefore, then the response x of t will be equal to the real part of the amplitude and e to the power I omega t, right. So, of course, the harmonic force is actually, let me write here, correct this is equal to the real part of this. So, let us say this is the harmonic force, which actually is nothing but f naught cos omega t. So, if f of t is real part of f naught e to the power I omega t, then the response will also be real part of x of omega e to the power I omega t. This is something we have done earlier, we explained a method of complex exponential to find the response, right. This is similar to that. So, before we proceed further, let us also try to find what is the loss factor and try to see how it is related with structural damping coefficient. So, the loss factor eta for the system would be equal to E d upon 2 pi in the energy at the beginning of the cycle, and for a system with structural damping, this is nothing but equal to alpha into a square, right, alpha a square, that is something we got, okay, and 2 pi and u is nothing but half k a square, that is nothing but the energy stored by the spring at the beginning of the cycle, okay, assuming that velocity is 0, and alpha is also equal to pi h. So, we get 2 pi half k a square. So, this 2 cancels out, pi cancels out, a square cancels out, and therefore, we are left with eta is equal to h upon k. So, that is how the structural damping coefficient is related to the loss factor. So, therefore, we can modify x of omega as this k plus eta k minus m omega square, right, is equal to f of omega upon k into 1 plus I eta minus m omega square. So, now we can find out we can substitute this expression in the equation for x of t and then obtain the final expression for the steady state response. So, we have x of omega here, which is f naught upon k into bracket 1 plus I eta minus m omega square into e to the power I omega t. So, if you multiply by the complex conjugate of the denominator and divide also and then simplify, right. So, final expression would be this f naught. We can also divide by k and replace under root k by m by omega n square. If all that is done, then the final expression would look something like this: omega upon omega n whole square plus eta square uh, into e to the power I omega t minus beta, right. So, this beta comes because the numerator would be a complex quantity, and we can then represent it in the polar form. So, therefore, x of t becomes f naught upon under root of 1 minus omega upon omega n whole square plus eta square and cos omega t minus beta, where the beta is given by tan inverse eta upon 1 minus omega upon omega n whole square, that is nothing but the beta. So, also I think I missed the k here, this will be k if not by k, right. So, therefore, this basically gives us the steady state response. This gives us the steady state response. So, the steady state response, we can also, let us go to next page, we can also define the frequency response function now. For the single degree of freedom system with structural damping. So, the frequency response function is nothing but simply the ratio of x of omega and f of omega, right, which is basically the steady state response to the harmonic force at frequency omega divided by the harmonic force amplitude at that frequency. And from the results we got on the previous page, we can directly write this as k into bracket 1 plus I eta minus m omega square, right. So, this is one form of the expression. If we divide by k and do simplification, then we would also get a result in this form. If I divide by k, then 1 plus I eta minus m by k omega square, right, which can be written as 1 by k divided by 1 plus I eta minus omega upon omega n whole square, which can be then written as 1 by k divided by 1 minus omega upon omega n whole square plus I eta. So, that is nothing but the frequency response function. In the complex form, of course, this is in the complex form. So, but if I want to find the magnitude, then I can then do that by finding the magnitude of this complex quantity, right. So, this is nothing but a frequency response function. So, if you plot this frequency response function, then the magnitude of the frequency response function alpha omega is a function of omega. If you plot, then it is going to look something like this. And this peak, in the case of single degree of freedom structural damping, it exactly occurs where at value of omega n. And the phase plot is also like this. So, this is the phase of alpha omega. So, this is at omega n, and this phase is 90 degree where when omega is equal to omega n. Otherwise, after when omega is less than omega n, the phase is in the range of 0 to 90 degree. When omega is above omega n, the phase is in the range of 90 degree to 180 degree. So, this is basically the frequency response function. So, now what about the free vibration response? So, in the we looked at the steady state response, which was the response when a harmonic force was acting, right. In the free vibration response, basically it is in the time domain, right. Free vibration response is not at a certain frequency, it is means the frequency, the response is not harmonic, it is a decaying response, and there is no suitable model available in the time domain to represent structural damping. It is possible, for example, one may think that we can take the inverse Fourier transform of the frequency domain equation, but it is seen that the model which is obtained after transformation, it does not represent a physically realistic damping model, and therefore, the free vibration response analysis of a system with structural damping is challenging and is difficult. And for same reason, we found only the particular part of the response. We did not find a free vibration response or the complementary part of the response. So, therefore, free vibration response, response analysis under free vibration is difficult, because a suitable model for representing damping force is using structural damping is not there. So, therefore, is it possible to represent or define what we can call as an equivalent system with viscous damping? Okay. So, can we approximate or can we define a system with structural damping by a system with viscous damping? Right. So, because time domain response analysis is difficult, can we explore the alternative that if we represent a system with structural damping by an equivalent system with viscous damping, then because viscous damping system can be analyzed in the time domain. So, is it possible to define such a system? To do that, let us first define what is the damping coefficient, right. Equivalent. So, we already have found out equivalent viscous damping coefficient CEQ is equal to we found it as h by omega, and we also found the result that eta, right, is equal to h by k. So, therefore, we can write h in place of h, we can write eta k by omega. Now, if we define a damping factor or viscous damping factor, say zeta or equivalent viscous damping factor zeta EQ is equal to CEQ upon the critical value of the damping coefficient in the system, right. So, this would be equal to Ceq is nothing but eta k upon omega, and Cc is nothing but 2 under root km, right, which basically gives us eta under root k upon 2 under root m omega, and therefore, zeta Aq can be then written as eta omega n upon 2 omega. So, this is the result we are getting, right, that the equivalent viscous damping factor corresponding to a system with structural damping having loss factor eta is given by eta into omega n upon 2 omega. And what we see is that such a equivalent system with viscous damping should have a damping factor which is related to the frequency, right. It depends on the frequency of the motion. So, it means if we want to study the motion at frequency omega, then we have a corresponding equivalent viscous damping factor which depends on this value of omega, and therefore, for every omega under study, right, for every omega there will be a different viscous damping factor, or the equivalent system with viscous damping would be different if the frequency omega changes of the study. So, therefore, there is no unique equivalent system with viscous damping which can represent the system with structural damping over all ranges of frequencies. Okay. So, that is why we cannot have a unique single representation of of the system with an equivalent viscous damping system. However, what can be done is we can approximate at least such a system. So, if we choose or fix the value of omega at which the equivalence is derived, then we can use that over all frequencies with some maybe we can approximate it though with some error. So, because the damping is dominant in the resonance at the resonance frequency and around the resonance, we can take if we take let omega is equal to omega n, right, means the frequency of motion which matches with the natural frequency, right. If we take that frequency, then Ceq is equal to can be written as eta upon 2. So, this equivalent is now obtained and that can be used over all range of frequency, though there will be some error because this is only an approximation. So, if the loss factor is eta, the equivalent viscous damping factor would be eta by 2. So, in this manner I think we have now studied today the vibration of single degree of freedom system with structural damping. We can now stop here. Thank you.